Welcome back, everyone. For this afternoon session, we're starting with Csaba Szepesvári, who is going to bring in a new topic that we have not touched on so far in the workshop, but which is also very important in learning theory, namely game theory and the connections with online learning.
Thank you, Seb. I don't know whether it's game theory or not, but well, it's online learning, and the talk is really about how to trade off information and losses. It's about this very nice model that's called partial monitoring that has a bit of history that I will talk about later. What we are after is kind of like a nice and complete understanding of how to do this. We will see how far to some extent we're going to make some progress towards this direction. That's my premise, at least for the talk. But then you will see that there are many interesting open questions left. So for all the aspiring minds out there, this is a nice topic to work. So the title of the talk is the complete classification of partial monitoring problems, and this is joint work with Thor Latimore, who is also a deep mind, just like me. By the way, during the talk, if you have any questions, then please stop me. It's more important for me that we are at the same page than I get through all the little calculations and whatnot. Okay, so what are partial monitoring games? So that's the first thing that I'm going to talk about a little bit. Why do I think that this is fundamental to understanding trading off information and losses? And then what is this classification result that I'm talking about? And finally, I will finish by, hopefully we'll have time to sketch a proof for one crucial step of this classification result that was missing so far. So I will talk about that there was previous work, the classification was almost complete, and then there was some missing step, and I'm going to show you how to complete the classification today, and hopefully we'll get to the end. So what is partial monitoring? So partial monitoring, you can indeed think about as a game between a learner and an environment, and the learner is choosing actions, and the environment has its own action set. And as the learner chooses actions, the environment chooses actions, the learner suffers some loss. This is kind of the typical setting for also online learning. We're not going to make any assumptions about how the environment is choosing its actions. Mild assumptions, let me say that. But we're not going to make probabilistic assumptions, for example, about how the environment is choosing its actions. And so far, this seems like I didn't specify what the learner observes. So the big difference to many other forms of online learning and partial monitoring is that we are very specific and particular about that. The learner is having this feedback which has some structure. We want to understand how the feedback structure, the form of the feedback that the learner receives is going to have an impact on how the learner should act when facing this problem. To formalize these ideas, let's start with a very simple example, which is I call the pennies problem, so matching pennies, but with a cost. In this problem, the learner is being taught that, hey, you have 3 actions that you can choose, and it's going to be a sequential problem, so this plays on rounds. And the 3 actions are that you can have, you can say head, or tail, or you can say that you're uncertain, and you're seeking information. Okay? the environment has two options. So the environment choices at time t, so time goes by in discrete steps from 1 to n. And at time t, the environment is going to have its choice. Actually, let's think about that. The environment makes its choices ahead of time, so that's easier to think about. And the choices of the environment are conveniently denoted by agent t, heads or tails. Okay? This is an arbitrary choice by the environment. The environment can look at the learner's code, but it can't do anything else. It's an arbitrary choice. And as the game unfolds, sorry, I want to use a different notation. Sorry. Mixing notations is not really helpful, so I will just say that these are the choices for the environment. And in round t, the learner is said that if the environment's choice is y of t, then you're going to suffer losses as follows. If you choose action A, so A is one of these guys, and this action happens to match the choice of the environment, then you're good. No losses, 0 loss. Okay. If you happen to choose the action U, that means that you're uncertain, then you're going to suffer a constant loss of C, and C is part of the problem specification here. So this cost is positive. Okay? And otherwise, so if none of these happens, then your loss is going to be 1. Okay? So this is how much loss you're going to suffer in a given round. We sum up all the losses that you're going to suffer, and you will be compared to the best loss that you could have suffered had you known the sequence ahead of time. Okay? That defines the regret, and you want to keep the regret small. So far, this doesn't look very different from standard online learning. To be more specific about what is that the learner observes. So the observations of the learner in this penny matching problem are going to be as follows. The learner is going to observe nothing. It's like an indistinct symbol that it observes. If the learner happens to choose either the action head or the action tail. If the learner happens to choose the action that it's uncertain, then the learner is going to see the choice of the environment. Okay? So this is one particular feedback structure that kind of makes the game a little bit more interesting. And as I said, the goal of the learner is going to be to keep its regret small. So what is the regret of the learner? Is the total loss that it suffers minus the total loss that it could have suffered had it chosen the best action in hindsight. Okay? Yes?
The best constant action or sequence of action?
It's a best constant action. It's kind of like the basic setup.
And does that imply some restriction on C? Presumably, like you wouldn't choose U. The best isn't to choose U the whole time because.
Right. But it depends on the choice of C. If C happens to be 0,
yeah, but
if
C
is positive, then presumably you want to be conscious about how often you're choosing U.
But what's the best? This is just
We'll need to. We'll talk about this
okay.
a little bit later. Yeah. Okay. So this is the regret, and this is random because the learner is allowed to randomize. So here AT is the choice of the learner. in round T. And by the time the learner makes this choice, it already learned the previous feedbacks, but it didn't learn anything else about the choices of the environment. Okay? So the learner is kind of told the structure of the game ahead of time. This is how things are set up with respect to the feedback and the losses. And then it has to decide about what strategy to use a strategy, minimize the loss. And then the questions that we might ask, or we will ask, is that how will C, for example, the choice of C influence the learner strategy, right? So intuitively, if C is, yes?
Doesn't it also affect the comparison as well? Because the best single A could be U, right?
Oh, the best single A will be U if C is, I said that C is positive, but if C was 0, for example.
Yeah, but even if it's positive, couldn't it be the case that the...
Yeah, so if C is positive and between 0 and 1/2, then it is possible that the best single action is U all the time.
Yeah, which is weird, isn't it?
I mean, that's how it is set up, right? I mean, the question is whether the environment would play such a strategy, right? Like, in the worst case, presumably the environment is not going to do anything like that. But that's really the question. So this is random, so we are going to care about the expected regret or high probability regret. And it's also important that this regret is pretty harsh, because you're comparing yourself to the all-knowing agent or all-knowing oracle that knows all the losses. And you can't possibly, in games like this, you don't have that knowledge even at the end of the game. Right? Like, it's really harsh to compare to that. So this will have consequences. All right, so more abstractly, the way the problem is set up, or you can set up, is that you choose two matrices. These matrices are going to define the game. So one of the matrices is going to be a 0-1 valued matrix. For convenience, we assume that the losses are normalized. Let's say the learner has k choices. So that's the cardinality of the action set. And the environment has e choices, capital E choices. Then you will be given this loss matrix. So this is one part. And the other one is that you have another matrix whose elements are coming from integers, because it doesn't really matter what encoding you use. It's like you could use any alphabet symbols. And this also has the same dimensions as the loss matrix. And you can encode a game like this with these two matrices as follows. So for example, for the pennies problem, what you are going to do is that you will have the rows indicating the choices of the learner, the columns are indicating the choices of the environment. So you will have heads, tails, and uncertain for the learner, heads, tails for the environment, and the loss is going to be 0 along the diagonal in the upper part of the matrix. Off diagonal it's 1, and if you're uncertain, then you suffer a constant loss C. And the feedback matrix has identical dimensions, and so here I said that I'm going to use integers, so I'm just going to say that in the first row, the two elements are identical. That means that if the learner chooses that action, it cannot distinguish between the two outcomes. So that means that the learner didn't receive any information. And in the final row, if the learner is choosing U, then the elements are different. So I can choose it to 1 or 2. There are many different encodings of the same. Okay. So in general, what we're interested in is that if you're given two matrices like this, an L and a phi matrix, I'm going to pair them up. This specifies a finite partial monitoring problem. Then I can ask the question, how should the learner behave in this game? How big is the regret? Okay. And this is the question that we're going to go after. So regarding the time, when do I start? 2:30. Okay. Great. So for those people who are familiar with bandits, if you, for example, just restrict yourself to binary losses, then you can encode all bandit games. You just have to have all possible loss patterns. So you're going to have 2 to the k choices for the environment as a result of this. And you make L equals to 5, so to say, and the learner that way is able to observe its own losses. So that's a bandit. A full information game. The learner, no matter what it chooses, it learns the choice of the environment. You can encode that by making sure that in the columns of the phi matrix, the feedback matrix, all the entries are different. If I choose something, then I can, based on the feedback, I can tell what was the choice of the environment. It's important to emphasize that these 2 matrices are given to the learner ahead of time. So they compute with these 2 matrices, things, and so on and so forth. Okay. So what's unknown here is the choices of the environment. Okay. One final example is dynamic pricing. That's up here. It's some version of dynamic pricing where maybe a charity worker walks door to door selling a calendar, and there is a unit cost assigned, like associated with just getting to the door, that's C, and then proposes a price for the calendar, and whoever lives there either accepts the deal if they think that the calendar worth that much money, or the deal worth that much money, then they accept the deal, and the revenue is subtracted from the cost. So the loss matrix looks like this. Okay? So here the choices of the environment are what is the price that the person living at the door believes is worth to pay for the calendar or for the charity. So the feedback in this case is going to be just sale or loss. So this is like a bandit problem. You can actually see your own losses, but you have some more information, right? Because if a calendar didn't sell for $3, it's not going to sell for $4. So you have a little more information. You can wonder about whether you can use that more information. So regret. So what we care about is the worst case expected regret. And that is nothing but if I take, let Rn be the expectation of R hat n. R hat n was this random regret. Okay? And this depends on the game. This depends on the strategy of the learner and also on the choices of the environment. Okay? So I can define the regret of a learner who is playing with a certain strategy against some choice of the environment in a certain game. And once this is done, I can look at the worst case regret that the learner is going to suffer and the best learner. So R and star in a given game, so this is specific to the game, is going to be the best of the worst case regrets. And what we care about is how this worst case regret behaves as a function of n, the number of points. So back to the penny machine problem. It's gone. Okay, surprise, surprise. So in the penny machine problem, if I make the cost big enough, if I make the cost bigger than 1/2, then you can convince yourself that the worst case regret is going to be at least n to the 2/3. Also, it's because the only way to gain information about whether the adversary is playing heads or tails is by using the uncertain action that has an excess cost of c minus 1/2 minus, okay. So we can think about the adversary playing a strategy, a stochastic strategy, of either choosing heads or tails with probability 1/2 plus minus epsilon. Where I'm not telling you at the time whether it's going to be plus epsilon for the heads or plus epsilon for the tails. So that's the remaining uncertainty that we don't know. In any ways, so the excess loss of using the uncertain action is going to be c minus 1/2 minus epsilon. You have to use that action epsilon squared time, and your regret is never going to be bigger than n times epsilon anyways. If you optimize this in epsilon n to the minus 1/2 minus 1/3 is going to optimize this, and you get that no matter what the learner does, it's going to suffer a regret of at least n to the 2/3. Okay? So what happens when c is smaller than 1/2? And you can convince yourself that, well, this is not a hard game. With a similar argument, you can figure out that the regret is going to be, in this case, n to the 1/2 square root n. And one question that is kind of left there, what happens to c equals 1/2? We'll come back to the question. So that's kind of a boundary case. Could go to c. Okay. So this is the sort of question that we're asking, but we want the answer to be more general. So I give you the two matrices, you do some computation, and you say that, well, the regret is going to be this or that. There are also games where the regret could be just 0. If you have an action that always wins, no matter what the opponent does, then that's it. That's very easy. So those are trivial games. And we also have games where, like you're given no information. So no matter what you do, you're not going to learn about the choices of the environment. There could be losses that make a difference. Those are impossible games, right? Those are the hard games. And so the classification result that I'm talking about is shown here. It is this theorem that says that if you give me a finite partial monitoring game, then the game is going to be exactly of one of 4 types. It's going to be an easy game where the regret is 0. It's going to be possibly a hard game where the regret is growing at least linearly, or the regret is growing like square root n up to a logarithmic factor, or it's growing like n to the 2/3, and there are no other possibilities. And we have seen pretty much all these possibilities happening already. Penny matching is kind of like a nice little entry example that shows that all these are possible. And the classification is, I say, that there is no other possibility. And it also tells you how, if you're looking at these two matrices, you can decide in an efficient manner which category a game belongs to. Okay, so this is the result that we are after.
Question.
And
high dependencies on K, E.
Right. Yeah. So there are some. So we are starting to understand the dependencies on. Yeah. This Landau notation hides all those dependencies very conveniently, and it was just focusing on the asymptotic regret in this way. And the problem-dependent constants, we understand a little bit of them. Like we know that, for example, dependence on F cannot be avoided in certain games. It's kind of surprising. Maybe first, surprising to me. But the understanding is that there it's very much lacking. So there is much to be done there.
And E also appears.
E doesn't appear. Yeah. It appears through F. It's F.
More reasonable.
Right. Okay. So the study of this problem, as far as I know, started with Cini in '99, who was really a game theorist, and trying to understand regret in games, and he was looking at Hanan consistency and used a refined version of regret that avoids this impossibility result. So you are less harsh in your regret definition. Pickup, Boni, and Schindelhauer came up with the first algorithm that for non-trivial, so trivial games are like trivially easy or trivially hard. For non-trivial games, you should get sublinear regret. They came up with the first algorithm to that achieves sublinear regret. It was n to the 3/4, and I learned about this problem actually from the book of Gabor and Nicolau and Gabor, and they done this nice work where they improved the result of Pickup, Boni, and Schindelhauer and proved that if the game is not impossible, then n to the 2/3 regret is possible. And then we became interested with the Alberta group and Hungarian Alberta group / Slovak, whatever. Around 2010, and we continued working on this classification, and we resolved the stochastic version of this theorem, where the environment is stochastic, and a major contribution was made by Foster and Brocklin, who transported our ideas to the adversarial setting, and we're going after this case. So this case was open, but there exists an algorithm for the sort of easy games that achieves the square root and regret. So they had a very ingenious novel design that achieved that, except that in the adversarial case, unlike in the stochastic case, there remains some gap. And the gap was exactly concerned with this case that for C equals 1/2, you kind of don't know what is happening. Okay. So now to give some content to this theorem, I will need to define a few things, and you have to bear with me while I'm doing those. And that's what I like to do, and then we can go after this, like what was missing, and how do we fill the gap. Okay, you good? Questions? All right. Right. So the first thing is that if you are in this penny matching game, what matters is ultimately you can think about the environment as playing a certain frequency each of its actions. Kind of when you're summing up things that only the frequency is going to matter, right? Like you have this linear structure. To bring out this linear structure, let me introduce some more notation, and I apologize for introducing more and more notation, but can't avoid it. So L of A is going to be a vector. It's going to be the row vector in the loss matrix that underlies action A. So the loss vector of action A. Right, so in the penny matching problem, so we have these three actions: heads, tails, uncertain. This is one of the vectors. This is the other vector. This is the third vector. So it has as many dimensions as the number of choices for the environment. Okay. So the environment choice so far was I of t, but I would like to use this linear algebra notation, so I'm going to introduce the unit vectors, the E of I unit vector. So E of I unit vector is the standard implement is always zeros everywhere except for the i's component. And with this, you can recode the game as having this linear structure. The opponent is going to choose one of these unit vectors. In round t, it's choosing e of I of t. Okay? The reason I do this is because then it becomes obvious that the loss that is being assigned to an action is just a linear loss. So it's LA times u of t. And it also becomes obvious that if you're thinking about the best loss in hindsight, you can move the sum inside. It's like the frequency with which the opponent plays the individual choices is what matters, right? So we start to think about this frequency space, the simplex. So the opponent is sort of playing on the simplex and moving around this thing, right? And then it's kind of obvious that at least you should understand where you should be playing if you knew in hindsight where the opponent's frequency vector lies. Okay? So this leads us to this definition of SAS. So if you take an action A, its cell is all those vectors on the simplex where the opponent plays. So this is my notation for the simplex. Minus one dimensional simplex, then action A wins. So what does this mean? It means that no matter how I try, my action A is better. It's actually easier. Okay. Write it this way, it's obvious that these are convex sets, convex subsets, those convex subsets of the simplex. If you think about what happens in a penny matching case, where the E-1 simplex is best represented with E-1 dimensional system, the orthogonal system, kind of distorted, but you can think about that this is the probability that the opponent is going to play hat. Okay, so there's the frequency with which opponent is playing hat. And this is 1/2, and you have, let's say, C, which is between 0 and 1/2. Then these cells are the following. If between 0 and C, the opponent playing this with very, the hats with very low probability, then you should play tail. So you're going to play tail. So here the opponent is making some mistakes, so you should play uncertain. Okay? And here the opponent is playing hats with very high probability, you should be playing hat. Okay? So you can do this more general, that's the SAS that you're gonna get. Right? And now you can see what's happening with this C. If you're increasing C, then what happens is that this cell in the middle collapses to 1/2, and then it disappears. At C equals 1/2, it exactly collapses to 1 point. It doesn't disappear yet. Okay, so this comes there, and then C equals 1/2, then you have like this single point cell. So here you should be playing tail, here you should be playing hats, and here you can choose to play tail or head or uncertain. Okay? All right. So these are these SAS, and if you have this SAS structure, you can define many things. So you can start to talk about, oh, my action is dominated if its cell is empty. So like if the cost is really high, the uncertain action in the penny matching game has an empty cell and it's a dominated action. Okay. Does it mean that you should never play a dominated action? Obviously not. We know that in penny matching the only way you gain information, but you're not playing it because the loss is good. You're playing it to gain information. When C equals 1/2, then you can play it because you think it's good, but it's like weird. Or you can just think that, oh, I need to gain information. That's the reason. The dimensionality of an action is the dimensionality of the affine hull of the cell of the action. And we call an action Pareto optimal if its dimensionality is E-1. So think about a game like this. So in this case, there are 3 choices for the environment. So we are on R2, and this is the probability of first choice, probability of second choice, third choice, just that. And so, sorry, frequency. And you can set up, for example, the losses in such a way that you will have these steps. 1, 2, 3. And these are Pareto optima. Their dimensionality is 2. And then there is this cell 4, which lies exactly at the intersection of cells 2 and 3. Okay? You can have those. Those are lower dimensional actions. We call them in our previous papers degenerate because we don't like them, so it's hard to think about them. And when c equals 1/2, then the uncertain action becomes a degenerate action. And you can have even like this action or even lower dimensional actions like 5. Okay? So the law structure allows all these. It won't allow, for example, that this cell has like it finishes earlier. We will have an lemma that says that that's not going to happen. Okay. So this is about the losses. Let's go back to some of these definitions. So we define Pareto optimal actions, which are potentially optimal and like have a significant cell. Degenerate actions are these, and we also need to introduce duplicate actions. Those are actions whose loss vectors are the same. You might think that, oh, then I remove one of those, but no, because the information underlying that action could be different, so it might be useful to keep those. So if you take two Pareto optimal actions, it turns out that it will be worthwhile to talk about neighbors. So two actions are called neighbors if the intersection of their cell is one lower dimensional than so it's E-2 dimensional. So in this game, for example, these two guys are neighbors, these two guys are neighbors, 2 and 4 are not neighbors. Okay? And obviously 2 and 1 are not neighbors. Okay? So the neighbors are the ones who are sharing a significant boundary, and we will need the set NA, which is A and its neighbors, and the set NAB, which is a little bit weird. So these are all the actions such that the intersection of the cells of A and B lie inside the cell of C. Okay? So these are actions that if you kind of like thinking about the opponents playing around the boundary between A and B, it's not that hurtful to play them. Right? Because the intersection is subset of the cell of C, so C is winning there in the intersection, right? Could be winning more. But, yeah. So in this neighbor set, there could be degenerate actions, like here, this 4. And here I can't show you any duplicate action, but you could have a duplicate action like that has the exact same cell as 2. That would also be included in the neighbor of 2 and 3. Okay. Okay. So these are the concepts that we need for the losses, like based on the losses, and how about observations? So think about how to use the observations.
One question. Yes, sir. Duplicate actions, they're not considered neighbors, right?
Duplicate actions could be neighbors.
Okay.
Yeah.
But
like you could have, like, you could have another action that's not called 2 that has the exact same cell. Let's call it 2 prime. That would be a neighbor of 3.
that would be yes, but they're not neighbors of each other.
They are not neighbors of each other because, doesn't. That's right. They could act as neighbors for other non-duplicates. Okay. All right. So, what's the role of feedback? We want to gain information. How can we gain information? What should we learn about? well, you might think that you want to estimate your own losses, but you can cook up games where it turns out that it's impossible to estimate losses, but you can estimate loss differences. Okay? So it's not a good idea to try to estimate losses in general if you're thinking in general terms. You should think about estimating loss differences, because if you don't know loss differences, then kind of like you can't really decide which action to play better. So at minimum, you should be able to estimate loss differences. So if you're thinking about whose actions loss differences you want to estimate, it's the Pareto optimals, right? You don't care about the others. So if A and B are Pareto optimal, we want to estimate the loss difference under any play of the pawn. What do we have at our disposal? So these algorithms generally work by, randomly sampling an action from some distribution, and then they receive some feedback. So based on this, you have to cook up something that gives you the estimate of the loss difference for UT. Right? So you want to estimate this. So how do you do this? Well, the only information that you have is the action that you chose, which can take k different values, and the feedback that you have seen, which can take f different values. And you need to estimate some real value loss difference. So you will choose a function v that takes this form, and then you'll just choose this. Use this and hope that on expectation, this function will give you an unbiased estimate of the loss. And we know that it might be beneficial just for normalization purposes, or just to divide by the probability of choosing that action. It's just more convenient to do things this way. And so you hope that the expectation of this condition on the pass is going to be LA minus LB at UT. This loss difference. If you work out the math, this becomes this condition that the sum for all possible action choices, there are k of them, of V, C, and phi of C of I should be equal to L A minus LB at E of I. E of I for all I. Right? So this should work regardless of the choice of the environment. So this is a necessary condition for having an unbiased estimate of points. So if we want the game to be possible, then we have to make sure that, we have to assume that this is possible. And these functions, notice that they're specific to the pair of actions. So for each pair of actions, you are free to choose your function. Okay? So this is how you will be able to estimate loss differences. And so now there are two more definitions. Somehow it turns out that eventually what asymptotically that boils down is whether you can distinguish between whether one of the neighbors of two neighbors is better under the choice of the environment or not. So you care about neighboring actions. So we're going to define a pair of actions. First of all, globally observable or locally observable. I give you two definitions at the same time. If there exists this function v such that star holds. Okay. This is for the globally observable, and for the local observable, we require that this function be 0 whenever C is not a neighbor. And whatever feedback. So if you're able to choose the function in this way, then we say that the action pair AB are locally observable. Okay. Okay, then a game G. G is going to be called globally or locally observable if it's true that for all AB, Pareto optimal, AB is a pair is globally or locally observable. Okay. We are done with all the definitions. Okay. Okay, and then we can reread the classification theorem that says that no, we have a chance of understanding it. Let's come down. Right. So it says that the minimax regret is going to be 0 if there are no pairs of neighboring actions. So G, the game, has no pairs of neighboring actions. So recall that neighborship was defined from Pareto optimal actions. Okay? Obviously, that the game is easy. The second case is if the game has pairs of neighboring actions, and all of those are, and the game is locally observable. And the third case is when the game is globally observable but not locally observable. And the last case is if none of this happens. And as I told you, the gap, well, I didn't tell you, but kind of hinted on it, that the gap was concerned with degenerate actions. So the previous classification result said that if we have a game that doesn't have any degenerate actions, then this classification holds. And now we are saying this classification holds anyways. Okay? So there were two gaps that had to be filled. One was in the lower bound, but I'm not going to talk about that. And there was another one in the upper bound that's kind of more interesting of like how do you use the degenerate actions. And there we're going to start in the last 5 minutes from the algorithm of Dean and Sasha. So the neighborhood watch algorithm. And we're going to patch this algorithm, and then I will just maybe wave my hands, and you have to believe me that it really works. Okay. So we need an algorithm for the easy games. So these are the games that there exists at least a pair of neighboring actions, and the game is locally observable. Okay. So we're going to assume that this VAB is God-given for every pair of AB actions. And then we will try to see how to use these. So one idea is that the game can be decomposed into these local games. So you pick an action, which is Pareto optimal. Okay, so first of all, what is that?
Gone.
Seriously? You made a mistake? That's it? Okay. So I wanted to go back to that little example. So if you remember my triangle, there were the actions which were kind of useless, 5 and 6. Remove those actions. So those are the actions that you don't actually need to play ever. So you're going to keep all the rest. And so we're going to have two classes of actions. First class citizens and second class citizens. Conveniently, their set is denoted by A and D. So A has Pareto optimal actions only, and it's a maximum subset of Pareto optimal actions that doesn't have any duplicates. Okay? And the remaining duplicates go here, And also the degenerate actions go here that were not on there. So we have these two classes of actions, and these are the first class citizens, and these are Pareto optimal, they kind of cover the full simplex, and for each of them we define a local gain. Why a local gain is because we want to use our ability to locally estimate loss differences. Okay? That's special about the locally observable gains, that you just want to care about local loss differences. So when you have an action like this, then it has its own neighbors. So nk is the set of neighbors. And you will define an AXP3, and I'm not going to go into the details of that, an AXP3.P algorithm, so it's like a high probability version of AXP3. And you set it up with the loss estimates that you just use these as loss estimates, and you have to bias. Except that, well, you have to tweak a little bit things, so I will come back to that. But it's exponential weights here, and so once you have these, this defines this Q of T of K. So for every K action, you have a way of acting. You have a probability distribution over the rest of the...
The range of B doesn't matter.
The range of B is going to come up, obviously. Yeah, it will show up in the bounds. Yeah, I think it's linearly.
I see. So you know, okay. The range.
Yeah, it does. Okay. Right. So the big O notation is also like that. So you have this distribution for any k, which is exponential distribution, exponential weight distribution. No question is how do you merge this? And that's what I learned from Sasha's and Dean's paper, that you just take, okay, so you have to do something else with these actions. So you're going to define QTK for these actions as the uniform distribution. Actually, it doesn't really matter how you define it. So this way you have a Markov chain. So you can think about collecting all these, and you get this Markov chain Qt. So that tells you for any k, doesn't matter whether it's in A or D, what should be the next action, so to say, right? It's a probability distribution over actions. So you look at this, it's a Markov chain, and you say, oh, what's a stationary distribution? It's a good way of merging these local probability distribution. It's kind of like the harmonic way to merge these. So you're going to define this distribution, which is the stationary distribution underlying Qt, and the reason I define things for the degenerate actions, so the actions in D in this way, so that this is uniquely defined. But of course, P_T is never going to choose any actions from there. Okay. So this is supported on A. So we're not really making any progress because our problem was that we need to use these guys to gain information. So the next question is, how do you gain information? What do you do? And there the idea is that, well, is the sharing idea. That we do have this probability mass assigned to all these actions, and we are very happy with that. And we need to assign some probability mass to the actions in D. So what you do is that you say that, well, if you have an action in D, it's either a duplicate of some action, or it's a degenerate action corresponding to a pair of neighboring actions. Pair of neighboring actions, or the duplicate, or whose duplicate it is going to share some of its probability mass. Okay, so you're going to reduce the probability assigned to these guys who have this unpleasant sort of like friends in D. But you're not going to do it such that these guys would lose a lot of the probability mass. They can lose a constant fraction of that probability mass. And it turns out that that's enough, and that you can do that. But since I'm out of time, I won't be able to share the details of that. So the next step is to do a redistribution. So you take this, you do this redistribution, sharing the mass. Okay, so here, what is crucial, when you are setting this up, you could share the mass in many different ways. What's important is that you don't want to lose on the losses. So you have this additional constraint that on expectation, under this distribution, no matter, right, so under, like, no matter what outcome the opponent chooses, the losses are the same. So this distribution will have the same expected losses. And there is a very useful lemma that we previously knew about, which said that if you have a degenerate action lying in between two actions, then its loss has to be the convex combination of the losses of those two actions. So we use this to design this sharing procedure. And you do this sharing, and you're not losing much probability mass. The loss constraint is satisfied. And then you have to mix uniform distribution, add exploration, and then one last little bit that really comes from the analysis. So when you're estimating loss differences, so to complete the picture, I need to define what loss estimates I'm using for the local gains. And there, I'm going to use smooth and loss estimates. So this P tilde distribution is going to say that for this action case, so for every local gain centered at K, I need to estimate the Ka differences between the loss of neighboring action A and action K. And I'm not going to just use that, but I'm going to smooth it with P tilde of T of K. Because if this was an unimportant action, then I can reuse the variance this way. And it's really, with this Markov chain construction, it nicely works out. So that's the loss estimate. This is the loss estimate that you use. Okay? And then you just add this beta term to guarantee that you have a high probability regret, and then you can complete and you have to press on that. Okay, I need to stop. So what's left? Well, as we started to discuss, there is very, very little known beyond this basic classification of how the various aspects of the regret are impacted by the choices of these two matrices. So I told you that we figured out that, for example, the cardinality of the number of different feedbacks is going to matter. You can cook up a game that shows that, but beyond that, we know very little. So thank you.
So the A and D sets, it sounded like in the degenerate case, where you had duplicate actions that were Pareto optimal, exactly the same losses, but potentially very different information revealed. You could put an uninformative one in A, and you still don't need a fraction in the one that goes in D. I mean, it seems like, this seems surprising, right?
So this goes back to that I'm hiding constants there.
I see.
So there will be this constant, which is the supreme norm of the V's that I'm going to get there. So these choices that were arbitrarily solved are going to impact the regret, and the regret bound kind of shows how. So for every pair of neighboring actions, you can take the supremum, like the largest value of V, right? So the variance is going to be impacted by that.
So the distinction is between just what's revealed. The feedback matrix close to the losses are all the same.
The V is about the feedback.
V is
about the feedback. That's the estimation.
Yes.